Jnanam Paramam Dheyam. Knowledge is supreme.
Okay, so that proves. So I want to give couple of remarks on this proof, and then we will start deducing the corollaries. Okay. So the first remark is, remarks. First one is, see here in this proof we have never used any special structure of the field K, whether it is finite, infinite and so on. It works for arbitrary field. If moreover, if you assume that K is an infinite field, if K is infinite, then the change of variables, the automorphism we have defined, here it was not linear because it depended on the gamma i's. The gamma i's could be bigger. So, but in case of infinite field, one can choose linear change of variables. Okay, for future use probably I want to say a little bit more. So, this change of variable term. So, for example, when one says an affine transformation of the polynomial algebra in and not necessarily over a field. So, allow me to use arbitrary base ring, because what we have used it for a field, but the definition makes sense for arbitrary base ring of R x1 to xn. Affine transformation of the polynomial algebra over R means it is a map automorphism of special type x1 phi, which is given by like this. So, let us write small capital X as the column x1 to xn. So, if I want R automorphism, I just have to give values on capital X's. So, I just have to tell you where this column goes. So, this column let us say goes to A x plus B. B is also B1 to BA, and where this A is a matrix AIHA, this is a matrix, it is in GALN R. The clear? If the matrix is in GLN R means it has inverse. So, over a ring it's complicated to check whether a matrix is in GLN R. All that we have to check is determinant should be a unit in, determinant of A should be unit in R. In case of field, we just have to check it is a non-zero constant. So, such automorphisms are called affine transformations of the polynomial algebra. So, for example, if you take a matrix A to be the identity matrix En, then this is a translation, then it is phi is a translation. and on the other hand if B is 0, then it is linear. See, in our case it's B is 0, but it is not linear, right. So, these are not the automorphism we have given in the proof of the lemma, that is not of this type. But if you take, if you assume your field to be infinite, then you can actually choose such a transformation actually. So, K infinite, then you can actually choose, then you can take phi to be what is called simple linear. So, the matrix, so to give such a transformation I have to give a matrix. So, in that case you can take the matrix like this, A equal to diagonal 1, below it is 0, and here you can take minus A1 so on minus an minus 1. So, that simply means you can take yi to be equal to xn minus ai no xi minus ai xn, I is from 1 to n minus 1. See, we have taken in the lemma xi minus xn power somebody. So, if k were infinite, then you can get away with the small such linear ones, and clearly these matrices you can see it's a nice matrix. Such transformations are called simple. In general, it is the group of odd, if I write this odd even for field k x1 to xn as K algebra. So, K algebra automorphisms of the polynomial algebra over a field in n variables, this is a group, and this group is very complex to understand. For example, it is easy to see when n equal to 1, what are the automorphisms of K algebra automorphisms of polynomial ring in one variable, that is very easy. They are just affine linear ones. They are of the type x going to Ax plus b and A is non-zero. So, that is very easy to check for n equal to 1. Already n equal to 2 it is a difficult task, and even n bigger equal to 3 it is even more difficult, and even n bigger equal to 3 it is an open question. So, what is the structure of this group, and n equal to 2 is also quite difficult, but known. Okay. So, now let us draw some consequences already from the classical version, and then we will go on to prove the more complicated one which is due to Nagata, which was proved in 60s. So, 9. Okay. So, consequences. These consequences have a lot of geometric meanings also, but I want to do that geometric meaning after I have little bit language from the geometry. So, today there will be only the algebraic consequence written in terms of algebra. So, corollary 1, this is one form of, this is also called algebraic version of Hilbert's Null-Stellen-Zatz. So, Hilbert's Null-Stellen-Zatz, this is, I will abbreviate it as HNS. and just I will give some number 3. This numbering comes from the way I have arranged the lectures some time back. So, this is also called Zariski's lemma. It says if you have a field extension, L over K is the field extension, and L is finite type over K, L is algebra of finite type over K, then L is actually finite, L is finite over K. So, in particular algebraic, over K. Finite extensions are algebraic. So, proof. All right. So, by NNL, L is a finite type over K, therefore, by NNL there exist elements Z1 to Zm such that L is integral over the subalgebra generated by this, and these elements are algebraically independent. So, there exist Z1 to Zm algebraically independent over K with L containing this is integral. L integral over K Z1 to Zm, but L is a field, this is a field, and this is a polynomial algebra, and if a field is integral over some ring, then you would have seen that that one is also field. So, therefore, this is also field then. So, this is a field because it is integral. But when can such a polynomial algebra be a field? The only chance is when M is 0. So, that implies M is 0. And so, that means L is integral over K, but integral in case of a basis field, then it is same thing as algebraic, but and it is finite type. Finite type algebraic is finite. So, finite type, actually finite type plus integral, this is equivalent to finite. Okay, the next one, corollary 2. Suppose A is finite type, A is K algebra of finite type, and suppose M is a maximal ideal, M belongs to SPM A, then the residue field A by M is a finite extension of K. Proof. See, A is a K algebra of finite types, A is here, this residue field is A by M is here, K is here, K is contained in A, this is finite type. So, therefore, this is also finite type over K. The images of algebra generators of A will generate A by M as an algebra. So, if this is generated by these small elements x1 to xn, then the images, further images they will generate A by M. So, this A by M is also of finite type over K. And the earlier corollary says in this case this is an algebraic extension, that is what we wanted to finite. So, by corollary 1, A by M is finite over K. Okay. Corollary 3. So, this I will call, this is also called weak form of HNS. I will not give the number now. When I write the notes, I will give the numbers properly. So, this is weak form. K is an algebraically closed field. Then we have a map from K power n to SPM of K x1 to xn. Maximal ideals in K x1 to xn, namely if I have a tuple A is A1 to An, then map it to MA. MA is the ideal generated by x1 minus A1, xn minus An. Note that clearly this is a maximal ideal. That is because the easiest way to see that is, let me go to the next one. So, the easiest way to say that, look at the evaluation map K x1 to xn to K, and the K algebra homomorphism is xi going to ai. This is a K algebra homomorphism. And kernel, let us call this as epsilon. Kernel of epsilon is precisely generated by x1 minus A1, xn minus A, and it is clearly surjective. Therefore, this mod kernel is actually the residue field is K. So, it is not only maximal ideal, but its residue field is K. Okay. So, we want to prove this map is, then the map is bijective. That is the assertion. So, proof, this map is clearly injective, Simply you have to check that the ideal generated by x1 minus A1, xn minus An, and if you take a different point xn minus B1, xn minus Bn, these are different if A equal to A1 to An is different from B1 to Bn. This is clear because if they are different, at least one of the component is different, and then the difference, if these ideals were equal, then both it will contain both the polynomials x1, let us say without loss, A1 is different from B1, then this, if they were equal, then this and this polynomial both are there. So, their difference is there. So, A1 minus B1 is there, but A1 minus B1 is different than 0. So, it is a unit and therefore, it is not possible. So, clearly it is injective. Surjective because if because look at the map K x1 to xn. So, take any maximal ideal M and look at this map K x1 to xn and then go mod it. This is a natural surjection, and then we have by because K is algebraically closed, we are assuming this extension is algebraic, that is what we have proved in corollary 2. because this is algebra of finite type, this is maximal ideal mode. So, this is finite type field over K, but K is algebraically closed. So, there is no algebraic extension other than itself. So, it is equality here. But then you can, there exist A1 to An in K such that they are the lifts of this. So, xi minus ai or xi is congruent to ai mod m, but that is equivalent to checking that this point ideal Ma, I wrote no, did I write the image? This Ma is contained in M, but this is maximal. So, equality here. So, that proves that each maximal ideal is coming from a point. Such maximal ideals are called points. So, I think it's a time we will stop here, and I will continue more consequences in the next time, because we should see the power of this normalization lemma. So, one more lecture I will need for consequences, and then we will go on to the more stronger version of normalization lemma, which is due to Nagata.